capacitors and how capacitors work, the E field they generate, and things of that nature. But today we're going to look at capacitors in circuits and how that works out. So we already know that for a capacitor, the voltage drop across the capacitor is equal to the charge that accumulates on each plate over the capacitance. So let's look at what happens when we have capacitors, multiple capacitors in a circuit. We'll look first at them in parallel. A capacitor is two horizontal lines, two parallel plates. That kind of makes sense. So if we have, we have our three capacitors here in parallel. Okay, and let's think about what's the same. Well, just like our resistors in parallel, this point is at the same voltage as this point, and this point is at the same voltage as this point. The voltage drop across each of these capacitors is the same. And we know from Kirchhoff's loop rule that if we go this loop, there has to be zero voltage drop. So the voltage drop across this capacitor is equal to the EMF of the battery. The voltage drop across this capacitor, if we draw this loop, is equal to the EMF of the battery, and so forth. So the voltage drop across each of these three capacitors is equal to the EMF of the battery. So we can say this, Q2, over C2, which is equal to Q3 over C3. All right. So if we consider the charge on each capacitor, we can rearrange this and we can say, that Q1 equals that EMF of the battery times C1 and so forth. So we can say the total charge of the circuit is Q1, which is epsilon C1, plus Q2, which comparatively is the EMF times the second capacitance, plus the EMF times the third capacitance. So the total charge, again, is the voltage drop across the battery times the C1 plus C2 plus C3. If we look at this, this is equivalent V equals Q over C, so V times C is Q. This is true. If we look at an equivalent capacitor, then we can say that our total Q is equal to the EMF times equivalent capacitance. So for capacitors in parallel, the equivalent capacitance is just the sum of the three capacitances. And to me, that kind of makes sense if you think about what would happen if these capacitors were actually touching each other. The areas would just all add up, and then you'd wind up getting one big capacitor that's, the sum of the capacitance of all three. So that's how kind of makes sense to me. Let's look at an example. Let's say we've got an EMF. Let's say our EMF is 12 volts. Let's say that C1, I don't have space to label it on the drawing, I'll just put it down here. Let's say that our first capacitance is 25 microfarads. Our second capacitance is 31 microfarads. And our third capacitance is, 14 microfarads. And I want to know the total charge stored on the plates of the capacitors. Keep in mind that the net charge on a capacitor is zero. There's a positive charge on the top plate, negative charge on the bottom plate, and that's what we call the Q in our formula here. But keep in mind that the net charge is still zero. There isn't, there isn't a net charge. So that's a simple matter. Finding the total charge, well, we know that V equals Q over C. So, and that's equal to, and for the whole circuit, we can say the EMF of the battery is equal to the total charge over the equivalent capacitance. So the total charge is equal to the EMF times the equivalent capacitance, which means that the total charge is equal to 12 times, and the equivalent capacitance, they're in parallel, which means that the capacitances will just add up. We've got 25 plus 31 plus 14 times 10 to the minus 6. And I can punch that into my calculator. And I take 25 plus 31 plus 14 times 12, e negative 6, and find the total charge. It comes out to 0.00147 as 1.5 times 10 to the minus third coulombs, which is actually a fair quantity of charge. So that's how we deal with capacitors in parallel. Now for capacitors in series, this was parallel. It's a little bit harder to think about what happens with capacitors in series. So let's see, we've got a battery, has some EMF, and then we have capacitor. I'm going to draw it this way because it will be the most space efficient, but you can see that all three of these are in series. This is capacitance 1, 2, and 3. Now for capacitors in series, to figure out what's the same here, it's important to remember that the net charge of the circuit is 0. Okay, the net charge of the circuit is 0. We can't just create charge from wherever we want to. All right, and so what winds up happening is that the battery creates this potential difference, and then electrons start flowing this way, even though our current is flowing this way, which means electrons are flowing this way. So this plate acquires a charge plus Q, whatever this charge is. The opposite plate has a charge minus Q. But this minus Q has to come from somewhere. And capacitors create a break. In the middle of this capacitor, there's no space. Electrons can't flow across the gap. Okay? So they're just moving around in response to this potential difference. So the electrons that show up to give this plate a charge minus Q have to come and flow up from this plate, which means that this plate also has a charge plus Q. And because it has a charge plus Q, it attracts this charge minus Q over here, which comes from electrons flowing off of this plate, which then gains charge plus Q, and this one gains charge minus Q. So the thing that's the same for capacitors in series, the charge on each capacitor is the same. And that's because of the conservation of charge. So the charge on each capacitor is the same, which means that the EMF is equal to, well, we take the voltage drop across the first capacitor, which is Q over C, over C1, and then we go across the second capacitor, and the voltage drop across that is Q over C2, and the voltage drop across the third capacitor is Q over C3. So the EMF is equal to that net charge times 1 over C1 plus 1 over C2 plus 1 over C3, which means that our equivalent capacitance, we can write this as Q over our equivalent capacitance. So for series, our equivalent capacitance is equal to, or 1 over our equivalent capacitance is equal to 1 over the sum of each of our capacitances. So you may have noticed that capacitors in parallel are like, they add like resistors in series, while capacitors in series add like resistors in parallel. All right. So let's do a problem here. Let's say we have capacitances, and I'll make them the same capacitances they were up top. We've got 25 microfarads. C2 we'll say is 31 microfarads, and C3 we'll say is 14 microfarads. And we'll say the EMF of the battery is still 12 volts. And I want to find the voltage drop across each capacitor. That's my task. Well, before we can do that, we need to figure out what the charge is on each capacitor. So we know that our EMF is equal to Q over the equivalent capacitance. And the equivalent capacitance, we know 1 over the equivalent capacitance is equal to 1 over 25 plus 1 over 31 plus 1 over 14. And these are each times 10 to the minus 6, and that's in the denominator, so we can say this is times 10 to the 6th. And we can punch that into our calculator, 1 over 25 plus 1 over 31 plus 1 over 14, E6, answer E6, and 1 over that, and we get that our equivalent capacitance is 6.95, etc., times 10 to the minus 6, so 6.95 microfarad, about. There are more decimals there. And then if we want, then we can find the charge, because we know that charge is equal to 12, is equal to the charge over the 6.95 microfarads. And we can punch that into our calculator, times 12. So the charge on each plate is 8.35, etc., times 10 to the minus 5th coulombs. And once we have that, we can find the voltage drop across each capacitor. So for capacitor 1, our voltage drop is Q over C1, which is at 8.35, divided by 25 e negative 6. And that comes out to 3.34, etc. volts. That's the voltage drop across the first capacitor. Voltage drop across the second capacitor is that charge over C2, which is just Q over, what was C2? 31 e negative 6, which comes out to 2.69 volts. And then V3 is that charge over C3, which is Q over 14 e negative 6. I'm running out of space down here. What? Error syntax. I put a random parentheses in my calculator, and shoot, I didn't put parentheses at all. Okay. Oh, okay, never mind. Which is 5.96, etc. volts. And if we add these three up, we should get 12 back. So this is, almost 6. So like this plus this plus this, the decimals will get us about 2. Plus 3 is 5, plus 5 is 10, plus 2 is 12. So they do come out. These decimals might not work out. Do they work out exactly? They do work out exactly. So the total voltage drop is 12 volts across the whole circuit.